Alright, this lesson is about radicals and graphs of radicals. We're going to review a bit about things we should know about radicals, a bit about transformations of functions, and apply them and put them all together. To start, some basics. The symbol that you see here is called a radical. It's also often referred to as a square root. We can also say that the index is 2. The index is the little number that sometimes appears, like in this case here, a radical with index 3, sometimes called a cube root. Now, there are different indices, and those values are always natural numbers. They're never 1, they're never 0, but 2 and upward all exist. Now, square root of 9 is 3, and this is called a principal root. This is a little different than x squared equals 9, where x would equal both positive and negative 3, which are square roots. So when we see the radical, we're only getting the principal root, the one that's the first, or the positive root. Excuse me. A check would be to say that 3 squared equals 9. Now, if the index is n, so if I said the nth root of a, where n is odd and a positive integer, or natural number, these can be evaluated when a is positive or negative. I'll show you an example in a moment. If n is even, for natural numbers, they can only be evaluated excuse me, when a is greater than 0. Examples are below. So the first two cases have odd indices. I can have a being positive or negative, and either one is capable of being evaluated. The justification is below. It has to do with the fact that an odd number of negatives is still negative, while an odd number of positives is positive. However, if the index is even, like a square root, and if I have a negative number inside, there is no solution to this. It can't be evaluated. The rationale is that whatever it's supposed to equal, when squared, can't equal a negative number. You can't multiply something by itself and get a negative number when you're talking about real numbers. So those are some basics. Now about terminology. Again, the n that you may see on a radical is called the index. If you don't see one, it's at 2. It is equivalent to a fractional exponent. So the denominator on an exponent. The a inside of a radical is called a radicand. And the result, or the thing that's equal to, is called the principal root. You can write either of these forms and they're equivalent to each other. Okay. The index is always a natural number, which is what this symbolism tells us. Okay, a review of transformations is next. So, applied to square roots, what I've done is I've used a graphing calculator to show the effect of negative signs. These are reflections. If the negative is outside the function, it's an effect on y. So this would be y2. If the negative is inside the function, the effect is to reflect over the x-axis. It's an x transformation. So this would be y3. y1 is the bold. You'll notice over on the left here that I've denoted y1 as bold. This is a thing you can do on your graphing calculator by moving your cursor to the far left and pushing enter one time. There's about 7 different options for graphing. You may want to experiment with that. Anyway, moving on, that's reflections. The next thing that I'll remind you of are translations horizontally. Notice that these values are inside the square root or the function. The y2 is a movement to the left, and the y3 is a movement to the right. Again, principal square root x as a reference is the bold. So this is horizontal translations. Next, vertical translations. Movement up is y2, movement down is y3. And lastly, some horizontal expansion, which is y3, and a horizontal compression, which is y2. This is a compression, this is an expansion. Consider the bold one and consider what we have to do horizontally. We move toward the y-axis. I shouldn't say move. We transform points toward the y-axis. See, that's half the amount. And y3, this would be off the scale somewhere over here. If that went too fast for you, you may want to put those into your calculator and experiment and pause the video and then come back. These are things that I would assume that you would know. Now, what do I do with multiple transformations? Well, we're going to do order of operations. Now, there's a couple ways we can do this. You've been shown how to put these together graphically one at a time, I'm going to show you something else that we can do. Consider y equals square root x. Good values to put in for x would be 0, 1, 4, 9, 16, perfect squares. Y would be the square root, or the principal root of these, which would be 0, 1, 2, 3, and 4. Now, this effect right here, number 1, is a vertical compression. So half of 0 is 0, half of 1 is half of 2 is 1, half of 3 is 1.5, and half of 4 is 2. Next, remember I can do vertical separate from horizontal. Step 2 is a vertical translation down 1 unit. So 0 is transformed to negative 1, negative 0.5, 0, 0.5, and 1. Next, because there's a bracket inside and it's factored, I'll transform by shaping horizontally first. That's a horizontal compression. So half of the x values, which look like this. Then lastly, I will horizontally translate to the left by 2, by subtracting 2. So, if I've done everything correctly, those are all my transformations, and what I plot is this x transformed with this y. So the point, negative 2, negative 1, right here, negative 1.5, negative 0.5, about there, 0 with 0, 2.5 with 0.5, and 6 with 1. 1, 2, 3, 4, 5, 6 with 1. Excuse me. That is my transformed function. You notice the overall shape of the square root x like I showed above, but in this case a lot of compressions and movements. Now the other way you could build this up is to write down the graphs after transformation 1, 2, 3, and 4, all on the graph grid, ideally with different colors or other symbols to keep it all clear. But that's transformations applied to a square root. Next, how to graph radicals that have higher indices. So we've talked about square roots so far for the most part. What do you do if n is a number bigger than 2 and a natural number? Well, here's an important thing to notice. Consider the inverse of y equals x to the m. The inverse then would be x equals y to the m. To isolate for y, I will take the nth root to remove the exponent n, which is what I've done on the next line. The nth root of y to the m is like saying y exponent n raised to the exponent 1 over n. So that's just y. Now, notice my result, this is my inverse of the function that I started with up here. The nth root radical is the inverse of y equals x to the m. Here's an example. Y equals x cubed, a cubic polynomial function that you've studied and looked at. Graphically, that looks like this. 0, 0, 1, 1, negative 1, negative 1, 2, 8, so very steep. And it's going to basically swoop in here and twist and dive like that. That's y equals x cubed. Well, we know how to graph inverses. Inverses have the points exchange. So 0, 0 becomes 0, 0. 1, 1 becomes 1, 1. Negative 1 becomes negative 1, negative 1. Those 3 points don't transform. But consider a point like this. This looks like about decimal 5 and a very small y value. Well, that would now be very small x value and decimal 5 on the y. And, oops, likewise in the negative direction. And I didn't graph it because it was off the scale, but I would have 2, 8. That would transform to 8, 2, somewhere over here. So what we get with the inverse is something like that shape. A reflection over y equals x, which is an inverse. So inverse knowledge coming into play. Moving on, how to graph y equals f of x versus y equals the square root of f of x for whatever f of x is. These are a little tricky, because we're going to have different domain and range due to the effect of the radical symbol. Here's a comparison. Y equals x cubed with y equals the root of x cubed. So f of x being a cubic function. Well, the domain is reals here. However, over here, I know with the square root that I need x cubed to be greater than or equal to 0. So that means x itself has to be greater than or equal to 0. Notice how the domain changed. Over here, the range, y can take on any real number. However, over here, I know that principal roots of index 2 radicals, or square roots, are always positive and at minimum 0. Again, the range changed. Let's apply this to a specific example that has a little more complexity. First, I'll just graph this so that you can have a look at what I just came up with. Again, here's x cubed, 2, 3, 4, 5, 6, 7, so about like that, there, and that's basically y equals x cubed. Now, y equals the root of x cubed. What I'll do is I'll put this on the graphing calculator so that you can see it. Let me get rid of this, and let's go x cubed and square root of that function. Now I'm going to show you a neat trick. Go to vars, y vars, right here, by right arrow, function by pushing enter, and choose y1, and close the bracket. So what we're doing here is we're saying whatever y1 is, we're taking the square root of that, which is square root f of x. It's kind of a neat trick. And let's go zoom 4. There's my cube root. Now, that's the square root of the cube root function. Not very intuitive. Let's plot that here. So it's here and here, but it opens more gradually after that. And I don't know if you noticed, but there's nothing over here because you can't have negative x and negative y. All right, last thing, I want you to graph y equals x squared minus 1 with the root of x squared minus 1. Okay, with f of x, the domain is all reals. It's a quadratic function. The range is y greater than or equal to negative 1. Remember, that's a quadratic function moved 1 unit down. Now, when it comes to square root, it's a little bit trickier. I need to say the content of the radical itself is at minimum 0. So x squared is greater than or equal to 1, which leads to absolute value x greater than or equal to 1. Consider a number line. This is often confusing for people. There's 1, there's negative 1. These are the values that make this statement true, x squared greater than 1. You may want to pause it and think about that. Now, let's graph those on the graphing calculator and see what we get here. So, we had x squared minus 1, and you'll notice that I've already got y2 set up really nicely because I'm referencing y1, and we will do zoom 4. Oh, and actually just before I do zoom, I'm going to do something here to make sure it really stands out. I'm going to go to y2 and I'm going to bold the y2 graph to make it very evident. Zoom 4, there's my parabola. Now, there's the function for its square root. Notice that the values of x are not allowed to be between negative 1 and 1, and the values of y are not allowed to be negative. So I'm going to just copy that, and I'm going to paste that right in here into your notes, and you'll be able to study that later. Okay, so this function right here and the other branch here, there's two branches, this is the root of f of x. All right, that's what's going on in this lesson.